Welcome you all. Myself Nagarajan, Assistant Professor in EC Department, Rohini College of Engineering and Technology. In this course, we will study about the biomedical engineering subject, embedded system and IOMT. When we embedded system designer design a embedded product, the set of protocols we needed to follow, that is yes, embedded system design process. First one is a requirements and specification. Under the requirements and specification, first one is a capturing requirements. We need to capture our customer requirement. The first step in the design process involves understanding and documenting the requirements of the system. This includes functional requirements and non-functional requirements. Tools like use cases, user stories, and requirement specification documents are often used to capture these documents. The next one is a defining specification. Specification is nothing but it is translate the requirement into detailed description of the system hardware and software component. Specification include performance metrics, interface description, safety standard and environmental condition under which the system must operate. And next one is a design and architecture. In the design and architecture, first one is a hardware architecture. So hardware architecture involves selecting the appropriate processor, memory and peripherals to meet the system requirement. This may include a decision on the type of microcontroller, memory size, communication interfaces and power management circuits. The architectural must balance performance, cost and power consumption of a required trade-off. When we designing a embedded engineer, these constraints are think about the when we designing a embedded product. And next one is a software architecture. Software architecture involves designing the software components including the operating system, device drivers, middleware and application software. The architecture must ensure modularity, scalability and maintainability with careful consideration of real-time constraints. And next one is a system partitioning. The system functionality is divided into hardware and software with a decision on what should be implemented in firmware and what in software and what in dedicated hardware like FPGA or ASIC chip. Effective partitioning can optimize performance and reduce power consumption. And next, implementation. So implementation is first one is a hardware implementation. The hardware design is realized through schematic capture and PCB layout followed by the fabrication of the PCB, that is a printed circuit board. Components are selected and placed with careful consideration of signal integrity, thermal management and power distribution. And next one is a software implementation. Software is developed using embedded programming language like a C, C++ or assembly language and tools like integrated development environment, that is a IDE. The code is written, compiled and loaded into the hardware with testing performed on simulators or developed boards before integration. This is the implementation process. Our next one is a and testing and validation. First one is a unit testing. Individual components like a hardware or software are tested to ensure they meet their specification and function correctly. Techniques include functional testing, performance testing and stress testing. These are the unit testing. Next testing is a integration testing. The system is assembled and the integration between the different components is tested to ensure they work together as intended. Testing scenarios often include system level functionality, real-time performance and communication between modules. The next one is a validation and verification. Validation ensures the system meets the user needs and operates correctly in its intended environment. Verification confirms that the system meets its specification and requirements, often involving formal method or simulation to prove correctness. Next process is a optimization. Under the first one is a performance optimization. The system performance is fine-tuned by optimizing code, improving hardware efficiency, and reducing latency. Performance optimization techniques include code profiling, loop unrolling, memory management improvements, and hardware acceleration. That is using DSP or FPGA. Next one is a power optimization. Power consumption is minimized by using low power components. When we choosing a low power components for our product, it is a power consumption is minimized. Optimizing software for energy efficiency and implementing power saving modes. Next one is a deployment and maintenance. Deployment, the final system is deployed into its target environment with the installation procedures ensuring proper setup and operation. This may include field testing, user training, and the establishment of maintenance procedures. The next one is a maintenance and updates. Ongoing maintenance including monitoring the system performance, diagnosing issues, and applying updates that like both hardware or software. Firmware updates are particularly important for fixing bugs, improving performance, and addressing security vulnerabilities. Hardware architecture. In hardware architecture, we want to define a processor core. In processor core, that is the first one is a central processing unit, is a CPU. The heart of the embedded system is responsible for executing instruction and performing calculation. Modern embedded systems typically use ARM Cortex RISC-V architecture, which offer a balance of performance, power efficiency, and cost. Our next unit is a digital signal processing unit, that is a DSP unit. It is a specialized unit within the processor for handling mathematical operation related to signal processing such as a filtering, FFT and modulation. Our next one is a memory subsystem. In the memory subsystem, we need to use a random access memory RAM, then read-only memory, ROM, then cache memory. So in a cache memory, a small high-speed memory located close to CPU to reduce access time for frequently used data. The presence of multiple cache levels improve overall system performance by minimizing the time spent accessing slower main memory. And next one is a input-output subsystem. In this input-output subsystem, we use a general purpose pins, peripheral interfaces. Next, in peripheral interfaces, we have two types of interfaces available. One is a serial communication interfaces and parallel communication interfaces. So, in this embedded system design process, we define the what are the requirements when we needed for a embedded engineer. First one is a requirements and specification, and second one is a implementation, testing and validation, and optimization, then deployment and maintenance. I hope that all of you understood about the designing of embedded process. Thank you.